Let's continue looking at basic Unix commands or skills that we all should have in the back of our pockets in the event that we encounter and have to work with and support Unix-based systems. So bring up a new invocation of the shell. This gives us an opportunity to use some of its features, including exclamation, to access the history. So we've talked our way through more and less pagers. Another interesting area is the notion of redirection, which is supported across operating systems, Unix, Windows, and others. And that is the ability to move input across as well as output across any sort of configuration that you'd like. So stringing together commands, moving things in and out of files, and so on. So let's label this one redirection. Now, in its most basic invocation, when you interact with the shell using a command to open, for example, a file, you're taking advantage of input redirection, which can be explicitly referenced using the less than symbol. So when you cat test, let's say 3.txt, for example, you are implicitly using input redirection. By virtue of running an application with an input file, you're using input redirection. That's the most common redirection. So input is simply referenced using the less than symbol or by default by calling input file. Now, each of the redirections or standards, if you will, in, out, and error are described in the dev tree. When we reference a file which is really on standard in, it's really the operating system's really making a reference to the dev tree. So /dev to the file descriptors directory. Notice there are three file descriptors, 0, 1, and 2. 0 represents standard in. So dev fd0 is standard in. So this is dev fd0 standard in. On the output side, which we can influence, which defaults to the screen, which is also referenced using a greater than symbol or double greater than symbol to indicate append redirection. This is considered to be output redirection. And by default is the screen. So when you run an application, it by default dumps its output unless it's configured to do so otherwise to the screen. And its file descriptor is located in dev fd1. And for each application that runs, there's also error or standard error. And this is referenced via dev file descriptor number 2. And we reference a 2 on the command line to access standard error. So for the most part, when we operate with applications, we're concerned about input, output, and error. The Unix file system and operating system maintains this all for us behind the scenes. So for example, let's see how we'd use some of this. When we cat the contents of a file, such as test3.txt, we could explicitly mention the less than symbol, which is the standard in, followed by test3.txt, and it behaves just as it would without or by omitting it. And on the output side, when we cat the contents of test3.txt, notice it's dumped to the screen, which is the console. In this case, our current console is dev sudo terminal number 1. But to send the output somewhere else, we use output redirection or append redirection. That restricts the output from our current screen or TTY to a file, for example. It's not restricted to a file per se, but it's often sent to a file. It could be sent to a name pipe or some other target, but it's often sent to a file. So we influence the output by simply using a greater than symbol or a double greater than symbol. To access error information, we reference the number 2. So for example, here are the files that exist in our directory. Supposing we're searching for test4.txt, which doesn't exist. Now that generates an error. That's your standard error. Test4.txt, no such file or directory. But how do we redirect the error? So we search for the bad file and we send the file descriptor number 2 to, let's say, some file named badfile.txt. And notice it doesn't dump the output on standard out this time, but the exit status is not 0 either to indicate to us that there was a problem in executing the command. Now when we cat the contents of badfile.txt, we see the error that was otherwise dumped to standard out. So the nature of some programs is to place the standard error message on standard out. So let's just note, some programs place stderr, which is dev file descriptor number 2, on stdout, which, as we've mentioned, is file descriptor number 1, so FD1. And that aids us, it assists us in determining whether or not programs that we've executed have been successful. Sometimes they're not, and it helps to know if the application can be verbose wherever possible. Sometimes it's advantageous for you to send standard out, for example, to a black hole such as dev null, because it may corrupt your target file, that you have an application parsing that isn't prepared to parse myriad errors. So one way to redirect standard out is to send to, for example, to dev null. So you search for a file such as one that doesn't exist, test4, and you send standard error, which is 2, to a place such as dev null. This redirects standard error to dev null. Now the exit status is still non-zero, but it doesn't create a bad file.txt. In fact, let's remove bad file.txt and rerun that. And now you'll see that there is no, well, first let's echo the exit status. So it's non-zero, and now let's check to see if bad file.txt exists. It doesn't. So, which of course generates an error. So an alternate usage would be, for example, LSL bad file sending standard error to dev null. So stderr vanishes. Anything you send to standard or to dev null, such as standard error, for example, disappears. So note, dev null is a catch-all which discards data. You can send anything you'd like to dev null and it'll handle it for you. So you're constantly thinking about input, output, and standard error. Largely input and output, and possibly largely output, since applications clearly spell out how they handle input. So it's largely a question of output that's of concern to us. Another feature that's of interest within the shell environment is the ability to chain commands. So let's discuss that briefly, command chaining. So for example, you'd like to run 3 commands. You'd like to cat the contents of test3.txt, and if that's successful, we follow that up with a double ampersand, which means logical AND. If it's successful, cat the contents of test2.txt. And if that's successful, cat the contents of test1.txt. Here's a way to execute 3 commands, although they seem to be related, but they need not be, to execute 3 commands with some sort of dependency built in for each recently invoked command. So let's try this out. So let's see what's happened. This is the contents of, or this represents the contents of test3.txt, test2, test1. Well, what does this all mean? Well, let's echo the exit status to see. Everything ran successfully. With command chaining, when separated using ampersand, it means the leftmost command must return an exit status of 0 for the following command to execute. So in order for cat test1.txt to execute, cat test2.txt must execute successfully. So ampersands, when used with command chaining, requires that previous command returned exit status of 0. So it's a quick way for you to chain together commands, and you can chain them as long as your shell will accept command line arguments. Another way to execute command chaining is to use logical ORing. So for example, the same command, cat test3, then test2, then test1, but the logic will change this time. What we'll say this time is cat test3.txt, or if test3.txt does not succeed, cat test2.txt, or cat test1.txt. Well, what's the difference in this case? One happens or the other, instead of one happens and the others. So it's logical ORing versus logical ANDing. So what's transpired in this particular case? The first command executed and returned 0, causing the subsequent commands not to run. So we have a means of executing commands as a logical OR situation. So this simply means run 1 or run left or right. So run cat test3.txt, and if it is successful, stop right there. If it fails, run test2.txt. And another test of that would be, for example, to cat badfile.txt, which does not exist. If that fails, cat test1.txt. So we see badfile.txt failed, which led the shell to run a cat on test1.txt. So we have logical ANDing and logical ORing. And the third way to run command chaining is to simply serialize your commands. So run all of the commands regardless of the previous command's exit status using semicolon. Let's try this out. This is a way for you to ensure that all 3 commands will execute regardless or without tying in dependencies between them. So notice in all cases they ran. How do we know? Well, test3.txt contains 2 lines, test2.txt contains this line, and test1.txt contains this line. So let's just note that the semicolon ensures that the dependencies don't matter or don't exist. So ensures that no dependencies between commands exists. That means run everything. So there are times where you need to run a series of commands regardless of dependencies across commands, and that's where you'd use semicolons. So insofar as command chaining is concerned, you have logical ANDing, logical ORing, and simply a serialization using semicolon, which can come in quite handy many times. Now there's still myriad other commands that are basic commands. Literally there are hundreds if not thousands of commands that can be referenced. Let's look at a few more that we like to interact with. So there are times when you interact with log files and they're simply just too long or carry on for too long and show you superfluous information. So this is where we can extract information from the beginning or end of a file that may prove to be much more useful than parsing the entire file using commands such as head and tail. We like to use these a lot because they're quite useful. So head, of course, extracts the first n lines rather than placing a strict number because it's subject to change, n lines from file. And conversely, tail extracts the last n lines from file. And this is all customizable, which is why we prefer to specify n so you can transport this where it makes our notes more portable. So let's cat the contents of test3.txt, which contains the following lines. A head against test3.txt returns everything because by default it's pulling out 10 lines. But what if you wanted just the first line? You could indicate return me just the first line. And conversely, what if you wanted just the last line? Tail n1 gives us just the last line. So head and tail both are quite useful. So head n1 file returns the first line. And insofar as log files are concerned, well, we know in var log, for example, there are a few files that we can interact with. So let's head var log xorg log. And there we see the first n number of lines. Usually 10 is the default. And conversely, that gives us, since log files are created in a serialized, chronologized fashion, this gives us a way of looking at the chronology directly using the first several items that were created in the file or the last several items. So head and tail, quite useful. Another important program is PS. This exists across all Unix-based distributions, Unix, Linux, etc. PS returns the currently running processes. Very important command. Often we invoke it as follows: PS with the AUX option or with the EF option. this returns all processes with users and more useful information. But let's show you what the output is when you don't elect to specify the options AUX or EF. By default, PS returns the commands that are owned by the currently logged in user. So if we run W, for example, this tells us that the user Linux CBT, or Unix CBT that is, has gedit and recently ran W. So there are two terminals open, sudo terminal 0 and sudo terminal 1. Well, PS revealed those various commands. So two bash shells are open with two PIDs or two PIDs. One happens to have the gedit process running. So PS with no options returns programs, and we should note all programs for current user, and it does not return programs for other users, whereas PSAUX returns all of the processes that are running on the system at the current time, which includes processes owned by other users on the system, including root and the various daemon accounts. As we scroll towards the top of the output, we'll see the column headers. So the leftmost column includes the user. Many of the processes were started by root to boot the system, including the init process, which is PID1, and the kernel itself, which is indexed at 0, as well as other useful information, such as the percentage of CPU that it's used, percentage of memory, the current memory that it's using, when the process was started, how long the process has been running, and the command that was used to execute the process. And this again spans all of the users logged into the current system. So across all processes, all daemons, etc. PS doesn't give us the authority to kill or to terminate or to interact with the processes on any other level other than a read-only level, which is why it's safe. But this also means that if other users are logged into the system running, let's say, commands with passwords in the clear, that could leak information unnecessarily. So PS AUX returns all the processes that are running now. Why is this useful? Because of course, just like with any operating system, you can see quickly which programs are occupying or using the most resources on the system. So for example, we see that the system's idle. It has an exaggerated value there. We see most of the processes are idle, doing nothing much. But there are times when you'll see rather busy information. Another process managing tool, which consolidates information from a number of tools, is top. So this returns PS, uptime, and memory usage information, among other data. Top auto refreshes. So simply executing top with no options will cause it to refresh, and you'll see in the output how frequently it refreshes. It appears to default to every 2 seconds, but again, that's configurable. It can be changed on the fly. So top shows us, for example, the last PID that was displayed, the load averages for 1, 5, and 15 minutes, the uptime of the system, which uptime returns, the number of processes running on the system, of which the overwhelming majority of the processes are sleeping, which is often the case on a non-busy system such as ours. CPU utilization, the nice levels, the memory, 360 megs are currently being used, although we've allocated more. The swap, how much is being used of swap? So this shows 522 megs of the swap is currently used, leaving the remaining free, which means we're possibly swapping a bit much. This is 53% swap, so we probably need to allocate more memory to the system. So that's something we need to look into to improve the performance and bring some of the CPU and memory values down. But also notice that it returns the same information, or very similarly formatted information, to PS, which includes the PID. It's rearranged in a different way. So instead of username being leftmost, PID is. So PIDs, username, the amount of memory it's currently using, the size, the total memory that it's taken. So Xorg, which is a hog, took 147 megs, but it's currently using 21.292 megs. And as you space, that forces a refresh on the fly. A number of options are included, which allows you to toggle and rearrange the column headers Just take a look at the documentation to get a sense with question mark, and here are the myriad options. For example, you can kill processes if you own them, if you have the privileges to do so. You can change the nice level of a process, which is simply the priority of a process, at will. You can toggle various titles, column headers. You can resort the output. A number of options are available. It's a largely self-explanatory tool. Our concern currently is to simply expose you to the tool. Another important tool that returns useful information, which we've already run, is df. This shows the partitions that are mounted. So returns mounted partitions. You'll largely see your local UFS and NFS mounts. You won't see swap. So we like to use df with the human readable format because that returns megabytes, gigabytes, etc. So df in its default incarnation returns 1K blocks. So with the human readable, gives us something on the order of megabytes, gigabytes, terabytes, and so on. Perhaps the most important column here is the capacity utilization. This gives us a sense as to what's in use. User, as we know, is low, which can also cause system performance issues. It's currently heavily utilized and only has this much available. But our other partitions are fine. The devfs tree is 100% utilized currently, but this is not an issue because it is a dynamic or in-memory file system that's maintained by the kernel for the sake of automatically provisioning hardware that's detected. The key is to follow your key partitions such as root, home, user, var, and so on, temp, to ensure that the utilization is what you expect it to be. And that's the purpose of the df utility. It's available across all these various Linux, Unix, and other types of systems. Now, another concept that's of interest that we should discuss before we move on to some useful tools is the ability to pipe commands. It's perhaps a very important Unix feature. Pipes allow us to connect the output, so connects output of left program to right program. This becomes quite useful. So we cat the contents of test3.txt, which of course is using input redirection. But using a pipe, we can then send that output somewhere else. So let's cat test3.txt. That returns 2 lines. But what if we wanted to do something such as counting the lines using WC or grepping using grep for a particular entry? That's where pipes become useful. So let's first cat the contents of test3.txt and count the number of lines using WC. Simple usage of a pipe, but quite useful for large files. So WCL, and this tells us quickly the file contains 2 lines. And how does this all work? We take the capabilities of one small Unix program and connect it to the capabilities of another small Unix program, and all of a sudden we have useful, meaningful data. So in this particular instance, we were not interested in the content per se, but rather the number of lines in the file. So for a large log file, we may want to know, does it contain 100,000 lines or 100 million lines? Well, this sort of combination of piping could achieve that goal. So again, normally when you cat the contents or run some sort of program like cat, it dumps its output to standard out. However, using a pipe, we've connected the standard out into the input stream of WC, which then was able to count the lines for us and provide us with useful information. WC does other things such as word count and otherwise. Now you can combine these sorts of programs to your heart's desire. So for example, cat the contents of test3.txt and grep the line that contains the number 2. So changing this, for example, and we're searching for 2. So one line contains 2. Then let's count that using WC. Well, why does this all matter? Well, let's go ahead and echo another entry into test3.txt, which reflects 2. So now test3.txt contains 2 lines that contain 2. So let's cat test3.txt, grepping for the number 2, which should return 2 lines. But let's say we didn't know that. Now we pipe into WCL, and all of a sudden 2 lines contain the number 2. Well, let's look at this again. We'll vi test3.txt and vary the data a little bit. So here's the data set, 1, 2, 2, and perhaps somewhere in the document we're going to, let's say, create some other entries, perhaps 3 or otherwise. Let's go ahead and WQ, bring this back up again. We did an insert. And let's sprinkle a 3 and a 2 and a 4 and another 2, 5, 8, 2, 9, 3, 3, 4, and maybe 5. Now we're not sure what the data set consists of, but we are still interested in the number of 2's that exist in the file. So if we cat the contents rather than eyeballing it, because it could potentially contain millions, if not billions of lines, we'll cat the contents, grep 2, and then count the number of lines that contain 2. So in this case, 4 lines contain the number 2. Now grep works by searching for the string that you provide anywhere on the line. So if you're interested in lines that, let's say, begin or end with the number 2, then you'll have to get a little bit fancier, perhaps using regular expressions. But for basic searches, we can quickly tell which lines contain 2. And for log file entries, we can quickly tell how many lines, let's say, contain log entries for a particular date. For example, when we look at var log, xorg log, these entries aren't all prefixed with a date, but we could grep the ones that do. Messages, for example, contains items, since it's syslog base, that have a date prefix. We could then use cat in combination with grep to find items that match a particular date. So piping is a very, very important mechanism. And you can, of course, pipe to your heart's desire. So you may connect an almost infinite, since nothing's really infinite, number of pipes. So when you think about how you connect the output and input streams of your various processes, you think about pipes as a means of connecting them together, and in particular for production apps. So the idea is that Unix utilities are small, nifty utilities. They do little useful things. That's always the case. Pipes make Unix the most powerful system you can access. So note, Unix tools are small, nifty, and powerful. In aggregate, pipes make Unix powerful. That's the whole idea. So if we have one program operate on your data set, another program operate on your data set, then all of a sudden the power is revealed. So for example, cat test3.txt. So the numbers aren't sorted. Well, sort is yet another command. Let's do a which sort. We'll cat the contents of test3.txt, pipe it into sort. Now note that sort rearranges the content so that it's numerically accurate. So it's sorted numerically. So as a separate example, cat test3.txt, piping the output into sort. And this sorts the content numerically because the data set represent numerical data. And of course, if it were alpha, then it would sort based on the alphabets as well. There are myriad Unix commands, myriad, literally hundreds if not thousands of useful commands. But armed with redirection, input, output, standard error, as well as append redirection, as well as pipes, and some of these small useful commands, you can get a lot done. Let's just note in this section that this is append redirection, and as its name implies, it simply appends the data to your file, so it doesn't clobber. So this does not clobber target file, whereas this is clobber redirection, and this does clobber target file. By clobber we mean it truncates the file. So if there are important data in that file, you will lose that data unless you have preserved it via means of backup or otherwise. So again, we've got pipes, input, output, and standard redirection, as well as append redirection. Utilities like top, ps, head and tail for looking at textual data, portions of it, cat for concatenating or simply dumping the contents, as well as many others, history, etc. Another one that comes to mind is file, which is able to interrogate a file and tell you the type that the file is. So uses magic numbers, we could just leave it at magic, to reveal file type. And this will detect correctly most, if not all, of the files available on your Unix-based system. So file against test3.txt will realize that it's an ASCII textual file, or if it's UTF-8 or whatever formatting or encoding is used for the file. And if you have, let's say, productivity files, let's say PDFs or others, OpenOffice, file will also properly detect the type of file. So that's a little bit about basic Unix skills. We don't want to spend too much time on this area. Just want to ensure that you have a good appreciation for what these tools bring to the table.